In this video series, we're going to study analytic one-forms in depth. These are going to be one-forms where we have a 1-0 form where the function here is analytic. So the first thing we're going to do is look at how to define integrals of these one-forms over just continuous curves, and we'll see that this is really just a topological object, basically. We're also going to talk about the fact that these integrals are invariant under deformation or homotopy of the path gamma. We'll also talk about special domains where the curves we have can be, well, if we have a loop, simply connected means that the loop can be deformed to a point, and so you get 0 for these integrals in that case, and also some other special properties. And then last we'll talk about Morera's theorem, which is a way to characterize analytic one-forms in a manner that only initially requires continuity of the function f above and a condition that the integral of f along all triangles equals 0. First, let's review something we've already done. So if we have a path or a curve gamma that's piecewise C1 and maps into a domain U, and I have an analytic function on that domain with a global antiderivative, capital F, then we can easily compute these line integrals of f over gamma by just doing a version of the fundamental theorem of calculus, basically, where I find an antiderivative, or I have one already, and I'll take the difference of the antiderivative at the endpoints. And this basically just came from a general chain rule for complex derivatives and the usual fundamental theorem of calculus. It's worth pointing out one simple corollary of this fact, which we might call the local Cauchy theorem, which is if I have a piecewise C1 loop mapping into a disk and an analytic function on that disk, then since we know that we can always find antiderivatives on disks just using power series, then I automatically know that for any loop mapping into the disk, I get that these integrals will be 0. Now, here are some important questions to motivate what we'll do next. Well, what if our function does not have a global antiderivative? How do you compute these line integrals? And what if the path is merely continuous? Is there any way to make sense of these integrals in the situation where gamma is continuous? So we're going to answer both of these questions, and we'll see that these objects really are meant to be defined on continuous curves, and that the sort of smoothness is just kind of an artifact. So let's look at this first with probably the most important example in this part of the subject. Consider just the function f is 1 over z, which is analytic on the whole plane minus 0. And we know that 1 over z does not have a global antiderivative on the plane minus 0. We could use the previous results to show that because its integral on the unit circle of 1 over z dz by our Cauchy theorem on circles gives that this is 2 pi I. If it had a global antiderivative, this would have to be 0. But it does have antiderivatives locally, and we had names for them. So the principal log is an antiderivative of 1 over z on the complex plane minus the negative real numbers. And we defined this log tilde. I don't know that there's a standard name for it. The logarithm that maps the plane minus the positive reals into the reals cross the interval 0 to 2 pi. So it maps into that particular strip as opposed to principal log, which maps into the strip r cross minus pi to pi. And this is a different antiderivative, but if you take these two sets, they'll give you the whole domain of our function, namely the plane minus 0. So using just these two antiderivatives, we can actually compute line integrals of 1 over z. And here's how we'll do it. So given a piecewise C1 curve mapping into the plane minus the origin, how do we compute this line integral of 1 over z dz? So here's the idea. What we'll do is take our interval and we're going to break it up into pieces so small that gamma restricted to each of those pieces will sit inside either the plane minus the negatives or the plane minus the reals. And kind of the picture to have in your mind is, well, if I draw a curve in the plane that misses the origin, well, let's say it starts here, and for a while it misses the negative reals. So I can say that it sits in the set C take away minus infinity to 0. But then eventually, maybe it starts to get too close to the negative reals over here. So then I'll just say that it sits inside of the plane minus the positive reals, and then when it starts to get too close to the positive reals, I'll switch to this, and I switch back and forth as I need to. So the idea is we can break up our interval into such small pieces that gamma restricted to these pieces will sit in one of these two sets on this tiny subinterval. And so I'll just say uj is my choice of whichever works for my tiny subinterval, and then I'll declare that capital Fj is log z in the first case or log tilde of z in the second case. I just need an antiderivative on these sets. And here's just some extra notation. Gamma j is this restriction to this interval, and zj is gamma of tj. So now that we've broken it up, so we have antiderivatives on each of these small pieces of the curve, then I can, in some sense, compute the integral of 1 over z over gamma, because I can break it up into these pieces, gamma 1 through gamma n. And then on each one of these pieces, I have an antiderivative, so I can use my earlier formula of I take that antiderivative of 1 over z, which in this specific case, we can use these logarithms, and I'll do the difference of these functions at the endpoints, so zj and zj minus 1. And so this gives us some way to compute this integral over a curve. And here are some general notes about what we've done here. The antiderivatives of 1 over z, or just any analytic function, are unique up to a constant when they exist. So these differences that we've computed, so a difference of values of an antiderivative, are independent of the choice of antiderivative because it's a difference of values. If I changed fj by a constant, then the difference of two values wouldn't change. And notice also that smoothness of gamma is used very indirectly. In fact, it's not. It's only used because we had this formula that I could compute the line integral in one of these small pieces by taking a difference of antiderivatives. But we could take this basically as a definition, and then we only need continuity of gamma. So these are general notes, not specific to this function, but if you think a little bit more about the function 1 over z, we also get some interesting observations. So here are some notes specific to this example. Notice we computed the line integral of 1 over z on gamma using a bunch of these differences of antiderivatives. And I'm going to kind of rewrite it because I want to compare these things all the way down the line. So I'll have f n minus 1 at z n minus 1 and fn at z n minus 1. So notice the f's are all different branches of logarithms. So here we're going to get a difference of the values of the log of z n minus 1. And so these are two different choices of logarithm of z n minus 1, and so they have to differ by 2 pi I times an integer. So when we rewrite the sum this way, sort of pulling off the end two terms that don't get put into here, I can write it as these end two terms plus these terms in the middle, where I'm comparing two different values of the log of zj, and so they have to be in 2 pi I z, so they have to differ by 2 pi I times integers. Okay, and we could also examine this here, that the real part will just be a difference of natural logs of the modulus, so I'll get natural log of zn over z naught in here, plus what we'll call the change in the argument of gamma, because this is basically just computing the change in angle as you move along the curve. And basically what happens is you'll have this part here, which will give you multiples of 2 pi, and this will give you some other change in the angle. But if the path here is actually closed, or if it's a loop, then this line integral over gamma will be an integer, because then this natural log term will go away, and well, and also these two terms will differ by 2 pi I, because zn would equal z naught if we had a loop, and so the difference here would be 2 pi I times an integer, and so here I've sort of divided out, so I just get an integer. And so this will be 1 over 2 pi times what we'll call the change in the angle or argument of gamma. And this is what's called the winding number of gamma around 0. Now let's sort of generalize what we've done here in order to give a definition of the line integral of an analytic one form that's essentially just topological.